2 now. This is still, I would say, most of review, although this section does have some stuff that's a little bit new to you guys. Starting off with graphing versus sketching, it's not really anything that's particularly notes. I just wanted to kind of tell you kind of difference in vocabulary. Whenever we graph, most of what we're going to be doing in here is sketching graphs. Sketching is where they're not necessarily perfect. Like what we did towards the beginning whenever we had that graph and we put the zeros on the graph and we were talking about the end behavior and how it went through different sections and bounced off like this. That was a sketch. That wasn't a full-fledged graph because we have no idea how far down this goes, what actual maximums and minimums are, or anything else like that. This is just a sketch. An actual graph is something, normally whenever we're doing actual graphing, we're going to use a graphing calculator. Because we want something that's very precise. To get something that's very precise, you're going to have to plot a lot of points. Now, to get something that's more precise, you'll learn how to do that in calculus. We're not to calculus yet. In calculus, you learn lots of things using derivatives and stuff on how slopes go, exactly where those maximums and minimums are. We're not to that point yet. So we're still at the point where we're doing a lot of sketching. We're going to figure out some important parts of the graph that are needed, but we don't have all the skills yet in order to get a perfect graph. So that's just kind of a quick note on that. We're not really going to, there's no work in the book about that. All right, intercepts. To start off with, where are your x-intercepts? X-axis. Okay, what's special about the x-intercept? In the equation, what do you have to do to find an x-intercept? Go ahead.
Zeros.
What's zeros?
Zeros and x.
No. Go ahead. Some equations you have to factor.
You need to find at what point y equals 0.
Okay. In order to find the x-intercepts, y equals 0. Right? If we're going to be on the x-axis, everywhere along the x-axis, y equals 0. So we do have to solve for x, but we can't solve for x in an equation if y still exists. So in order to get rid of the y has to equal 0. We could solve for y elsewhere if we set y equal to another number, but if we're interested in the x-intercept, y is going to equal 0. So likewise with the y-intercepts, they're on the y-axis, and x will equal 0. Now, there's going to be maybe a little bit in your book that's going to have you do it graphically, but most of what we're going to be interested in is for you to be able to do it algebraically. So we're going to be interested in you. If I give you a problem and ask you to find the y-intercept, that you know that you have to change x into 0 and that you know how to solve for y. All right, anyone still need that? So I'm going to do a couple examples. On these examples, again, I was rushing a little bit to get these done. I've had a busy morning. So on both of these examples, we're going to find the x and the y-intercepts. So in a test question, I would give you something like this and ask you to find x and y-intercepts. So if I'm finding the x-intercept, my first step is to set that y equal to 0. So we're going to start off with an easy one. Okay, then I solve that. In the interest of time, I think on this one, you guys can all solve that one fine. So x equals 10/3. Y-intercept, your first step should be to make x equal 0. So then y is going to be -10. Now, I guess technically, I'm not big on technicalities usually, but technically our x-intercept is an ordered pair, so this would be my x-intercept. This is going to be my y-intercept. On a test or anything, as long as you're stating that you're finding the x-intercept, if you say x equals this, I'm fine with that. As long as you're stating that you're finding the y-intercept, that's fine. As long as you label it, you're okay. I'm not going to get picky that you didn't put it in an ordered pair. You have enough other stuff to mess you up that you don't need me getting picky that you didn't put it in an ordered pair. Okay, so number 2, x-intercept. So I let my y equal 0. Cube root that. So x is -2. Cubes are fine. You can do odds. It's evens that you can't do. Now the other thing with that, let's say I did have an even and I square rooted. Can you have an I? Let's think about that real quick. Let me put that on this sheet of paper, just so I have a room to put it. Let's say that I found my x-intercept to be plus and minus 2i. Where am I going to plot that? No, because then they would be 2 and -2. Where are imaginary numbers on your graph? They don't exist on your graph, right? So whenever you're doing something, you get imaginary numbers. Let's say that you're dealing with a parabola, and you were asked to find the zeros of a parabola. Anytime you were solving and you got zeros that were imaginary, what that meant was that your parabola went like this. So imaginary zeros meant that you did not have x-intercepts. So when we're finding x-intercepts, if you get imaginary ones, that means that they don't exist. That's a good question, because that can occur on tests, and if you get those, make sure you write no intercepts. So that'll be something that comes up a little bit later. We can have imaginary zeros, but we cannot have imaginary intercepts. Okay, so if we do our y-intercepts, all right, so let's see, y-intercepts, I put a 0 in there for the x. Now, if I see that on your paper, you're going to lose points. What am I missing? The plus or minus. Whenever you introduce a square root into a problem, you have to put that plus or minus. So that means our y value has 2 square roots. So whatever this graph looks like, it crosses the y-axis twice. Yeah. It could. It could be, it would be 2 square root of 2. Okay. You okay with intercepts? Okay. Symmetry is the new topic. Now, graphically, normally everyone gets it. It's when we move to algebraically that people start having issues with it. So I'm going to try to take a little bit of time with it. Explain it graphically. Again, graphically, you're all going to go, yeah, this is easy. Okay, x-axis symmetry means that it's symmetric across. If you fold it across the x-axis, it would match up. That's what x-axis symmetry means. So, for example, if we had a parabola with its axis of symmetry across the x-axis, along the x-axis. My graphs are terrible, so pretend like it's symmetric with the x-axis. So if I take any point here and the equivalent point, this distance to be the same. Okay, y-axis symmetry. I'm just going to stick with our parabola. Same thing. If you fold it along the y-axis, it would match up, which means if you take any points at the same height, that distance has to be equal. Okay, symmetric across the origin is a little bit weirder. there's an example. If I take any point here, then the distance to the origin is the same. Okay, now, algebraically, what I'm going to do is I'm going to show you what this does with the ordered pairs, and then we use that to get it algebraically. So, as far as the ordered pairs go, here, if I have this ordered pair, which one of those two variables is the same? The x. Okay, and the y, how is the y different? It's just negative. Okay, and same sort of thing happens here, right? If this is xy, what's my other order pair? Negative xy. Okay, what do you think this one is? Yeah, negative x, negative y. Okay, so that's what we're going to do to test this algebraically. Okay, switch this. Okay, so trying to think of how I normally word this. I don't like how the book words this. Okay, if we have, well, I don't want to call them a function though, because they're not functions normally. I think that's decent. Okay, so we test, when we're testing for x-axis symmetry, we test it by replacing the y with negative y. Right? If you look back at your graph, whenever we have x-axis symmetry, if I put negative y in, I should get an equivalent point, right? So that's how we test it. So if I come down here and I want to test this equation for x-axis symmetry, what I'm going to do is I take that equation and I put negative y in there. And then I try simplifying it. If I can get it back to the original equation, then it has x-axis symmetry. Well, if I take negative y and I square it, I get positive y again. So this one checks out. It does have x-axis symmetry. So that's how we test for symmetry without having to go to the graph, because it's a pain to graph every single equation that we have to look at. Okay, so then we have similar rules for all the rest of them. If I want to test for y-axis symmetry, I'm going to test by replacing x with negative x. If blah, 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 blah. If it's equal to the original, then symmetry exists. Symmetry with respect to the origin. Now, some people get in the habit after they've done a few of these of saying, well, it's not going to have origin symmetry unless it has both x and y symmetry. That's not always the case. Do not get into the, you're going to do some of these problems and that starts to become a pattern. That's not always the case. So don't get into that habit. And then we have the rest of that. Okay, so if I finish this up down here, if I test for y-axis symmetry, I take y squared plus negative x equals 1. So I have y squared minus x equals 1. Is there any way I can make that look like the original? No. So it does not have y-axis symmetry. Okay, origin symmetry. Okay, is there any way I can make that look like the original? Yeah, well, no. So the highest can go. So that one's the same as the previous one. So that one doesn't fit either. Does it help if I scoot it over to this side? It has a minus sign that I can't get rid of. So if I would try to get rid of that minus sign by multiplying by a -1, then this would have a negative and this would have a negative. So there's no way I can turn that into a plus sign. So, and then this one ends up being the exact same. So the only kind of symmetry this has is x-axis symmetry. Okay, one more and then we're going to stop for today. because we still need to cover circles, but I know I'm out of time. Okay, so if I test this for x-axis, that one works. Okay, check for y-axis. Now, the other thing you have to be careful of is some people get in the habit of saying, oh, well, it has a y squared, so it's going to automatically. Be careful of that too, because just because it has vertical symmetry does not, or horizontal symmetry does not mean that it will have x-axis symmetry. Because if I put just a plus y in here, then it doesn't work anymore. Even though that means it has horizontal symmetry, it doesn't have x-axis symmetry. Okay, because the negative is inside the square, this one works out. Oops. And that one works out. So that one has all three of them. Yeah.
We have to make sure that X and Y axis work.
No, you can do them in any order you want to, because none of them rely on the other one. Like I said, I can show you one where the origin works and the other two don't. That one right there, origin works, the other two don't. All right. See you guys tomorrow.